Now we will focus our attention in a couple of backtracking strategies. We will walk through two important backtrackings. The chronological backtracking is the simplest of them. It's about going back to the latest choice point and try another choice when a partial solution cannot be extended. So here is what the chronological backtracking does. We look at this through our 4 queens problem. So we place our first queen, and then the only possibility is here now to place it either in the third or in the fourth column in the second row. So we place it here, and then we realize that we are not left with any legal choice for our third queen. According to chronological backtracking, we would now need to backtrack from here to the point where we could get the second choice. So we would backtrack from here, and we will look for using the other choice at this choice point, which enables us to have a legal value for our third queen. But if we go one step forward, we realize that now it is no longer possible to have any legal position for our fourth queen. So we would need to backtrack again, but that backtracking would be to the last choice point, which we have not yet exhausted. So this one is already exhausted, so we will go back here, and that would be chronological backtracking. This is something that we have also looked at when I was talking to you about the backtracking algorithm. Now we will look at one of a slight variance of this called the back jumping. So the back jumping, whenever we arrive at a dead end, it backs up to the most recent variable that illuminated a value in the current domain. So let us try to understand that with a 6 queens example. So here is our 6 cross 6 grid. Let us place our first queen in row 2. Then we place our second queen in row 5. And now the legal positions possible for our queen, we pick up one and place it in row 3. You should realize at this point that either I could place my fourth queen here or somewhere down there, here. So I take that option and place my fourth queen here. Now I am left with only one legal position for my fifth queen. I cannot place it here because this queen will be in direct attack. I cannot place it here, it will be attacked by this queen. I cannot place it here because this will be then attacked by the third queen. I have only possibility of placing it is in this position, and which is on the fourth row. Now I am looking for a position for the sixth queen. If I go for the first row, that's not a legal position because this queen will then attack. If I go for the second, this first queen will attack. If I go for the third row, I already have a queen sitting on the third row. I cannot use the fourth row, neither can I use the fifth or the sixth row. So I now do not have a legal move for my sixth queen. I do not know which position to place because I now have an empty domain. Now when I want to back up on this and go back, I would rather love to go to the most recent variable that eliminated a value in the current domain. So how do I go about doing that is I try to look at the earliest queen that conflicts with the squares for the 6th queen. Like, let me see what I mean by this in the given example. So if I want to now place something in this square, I would love to identify which is the queen that conflicts with the square for the 6th queen. So if I do this, I realize that it is my 2nd queen sitting there, which is actually not allowing a queen in the 1st position on the 6th column. Next, if you look for the 2nd position, you see it is the 1st queen. So I try to identify the queens that do not allow me these positions and try to record each of the earliest ones. So the 3rd position is covered by the 3rd queen. The 4th position is covered by the 4th queen sitting here. So that's the earliest queen that conflicts with the square for the 6th queen. Then for the 5th square, I have the 2nd queen, and for the final, I have the 3rd queen. I record all these queens, the earliest of them, and then I take the largest of these values. The largest of these values actually gives me the latest variable that conflicts with making the current domain empty. So I take this value, which is 4, and now I know that if I have to jump back, changing 5 would not help. I have to go back and look for making changes at the variable level 4. This is back jumping. Now, back jumping works only when the dead end is encountered during search. That's sometimes called the leaf dead end. If by chance, if you go there and you are not able to get an alternate value at the culprit variable, in our case the 4th variable here itself, that's called an internal dead end. Beyond that point, back jumping only does chronological backtracking. Now we will look at one more variant of back jumping called the conflict directed back jumping. We will simply introduce the idea here, and working through an example, I leave it as an exercise for the readers. The conflict directed back jumping is an algorithm that is aware of the underlying constraint graph. It determines where to jump back to based on the actual conflict that it has recorded. So it uses an ordering on the constraints and identifies the earliest constraint that violates it, and it maintains a conflict set for each variable, that is list of previously assigned variables that are related by constraint. When we hit a dead end, it back jumps to the most recent variable in the conflict set. Interesting is that it learns from a conflict by updating the conflict set of the variable we jump to. When a contradiction occurs, conflict directed back jumping, which remembers the minimum set of variables from the conflict set that was responsible for the problem, and takes a decision. In fact, it saves no goods variables as new constraints. This is better than simple back jumping, which had no such memory. So to conclude, we had looked at constraint satisfaction problems, which are an alternate formulation of problem solving. Each problem is represented as set of variables, set of constraints, which together specify a relation on all the variables. Solution is a specification of the allowable values for the variables. we have confined our discussion to only finite CSPs. CSPs whose domains are finite sets. There are many interesting problems that have infinite or real domains. We have not looked at them. We have looked at backtracking, which is a depth first search with one variable assigned per node, and then we add to it consistency checking. Variable ordering and value selection heuristics, we have seen, help significantly. We have looked at the idea of forward checking that prevents assignments that guarantee later failure. And then we have looked at constraint propagation, including arc consistency, that does additional work to constrain values and detect inconsistencies. Thank you very much.